Now we're going to look at the magnetic force on a current carrying wire. We are going to see that just as a charge, electrically charged particle will feel a force, charge going through a wire will create a force on the wire if it's in a magnetic field. So again, we saw previously that the force on a moving charge was equal to Q V cross B. Again, we can think about a wire as carrying different charges and the current being related to how much charge is flowing through that wire per unit time. Let's look at this wire right here. The magnetic field, as it's set up, is going into the board, and there's no current going through this wire, so essentially all the charges are stationary. Without any moving charge, there's no velocity of any charge, and thus the net force is going to be zero. However, now, if we have the current going in this direction, that would be the same as having positive charges with a velocity in this direction here. Okay? So we're going to do V cross B. B is into the board. V cross B using the right-hand rule. And that creates a force in the negative x direction for this. We reverse the current, we get the reverse effect. Now we have the current going downward. V cross B gives us a force in the positive x direction. So clearly, if we just view the wire carrying current as a pipe carrying charge, it's really not different from the previous case where we had a single charge and a force on this. Now we have a flow of charge and an associated force on this. How do we calculate the force on current, however? Well, again, we already saw how the right-hand rule works. If the current is going in this direction, it's like we have positive charges going in the positive x direction. Again, V cross B gives us a force out this way. In a wire, we actually have negative charge, so the negative charge would be going in the opposite direction, but it would still give us the same direction for the force. Okay? So, this is sort of an artificial way of viewing what's going on. It allows you to use the right-hand rule. Now, current is equal to the number of charge carriers per unit volume times the charge per charge carrier. If they're electrons, they're going to have an elementary charge, times the cross-sectional area, A, times the drift velocity of the charge carriers, in this case the electrons. So we can say the infinitesimal force on each small bit of charge is going to be equal to the charge density times the area times the infinitesimal length. So that gives us the total charge that is going to be contained in some infinitesimal length of wire. Okay? We multiply that times the elementary charge, which is how much charge each of these have. So again, that's giving us the number of charges times the elementary charge in that infinitesimal wire. And then again, we have V cross B, which is what we had in our original equation. Okay? Now, for V, we can make a bit of a substitution here. Instead of having V cross B right here, since the length of the wire is in the same direction as the velocity, we're going to switch out this. We're going to say the infinitesimal bit of wire right here is going to replace the V in this cross product. Okay? And again, we can do that because the velocity was in this direction and the length of the wire is also traveling in that same direction. All right? And then finally, we replace NEA times VD with current. Okay? So if we look at this and we integrate over the entire wire, the the force on that wire becomes the current times the length across the magnetic field. So this is not unexpected. This is sort of what we would expect, that the force becomes greater as the current becomes larger, the force becomes greater as the length of the wire becomes greater, and the force becomes greater as the magnetic field becomes larger. Again, the cross product comes into play because if the length of the wire and the magnetic field are perpendicular to one another, that'll maximize that angle at 90 degrees, that'll maximize theta, sine of theta. So again, the force on a wire is equal to the current L cross B. If we want to just simplify it into much, into its scalar form, it's just current times length times magnetic field times sine of theta. Again, the magnetic force is exerted on each moving charge in the wire. So the net force that the wire gets is really the summation of all those individual forces. And again, total force is I times LB sine theta.